What's up? We're just gonna wait a few minutes, give people time to join, and then we're gonna get started. Hello. Thank you. Yeah, they look sick, dude. Like, these look so nice. Like, look at this. And then isn't this one? Hello. Yeah, so we just dropped the NFTs. If you guys are freshman graduates, um, it's already in your accounts, bro. If you guys are like freshman graduates or whatever, you'll see that we have 300 and 306 freshman graduate NFTs owned by a bunch of people, and then we have about, I think, like 40 or something. 41 sophomore NFTs. They're already in your oh, yeah, they're already in your what's it called, in your wallet. How do you get these NFTs? So if you are a graduate from any one of our tracks, if you graduated before last night and you had your ETH wallet linked on the website, we just airdropped these to you. So we will do like airdrops probably like once every month. And once every month, everyone who graduated will get these NFTs airdropped to their wallets that they linked on the website. So if you were a freshman graduate, you probably already have them. If you're a sophomore graduate, you probably already have it, assuming you graduated before last night. All right. Um, okay. Um, it's not on Etherscan. Um, it's not on Etherscan. The NFTs are on Polygon, so you have to check polygonscan.com. Um, we cannot airdrop on mainnet because that would cost us thousands of dollars to send it to hundreds of people. Um, how do you track who has graduated? Well, I mean, if you're on the LearnWeb3 website, we ask you to link your wallet we ask you to link your ETH wallet, and we can see if you've graduated or not based on like if you've passed all your skill tests or not. So we can figure out all the users of the website who have passed all the skill tests, and if you linked your ETH wallet, then you got the airdrop. We tell you that you connect your ETH wallet so that you can get graduation NFTs. Um, so that's how we figure it out. Yeah, different dApps can track them in different ways, but um, yeah, that's how we did it. We just checked all the users of the website who have passed all the skill tests for a given track, and if you had an ETH address linked, then we sent you the NFT. OpenSea is so laggy. It still says there's only one item when there's clearly like 2 NFTs here. Yeah. All right. Oh yes, it's possible. Um, it's possible, yes, that your NFTs are hidden. If you go to your profile on OpenSea, they may be under the hidden category. Um, Sometimes random airdrops, OpenSea places them in the hidden category to let people like just in case it's like spammy. Like I have a bunch of spammy NFTs. Um, so they might be in your hidden category if you don't see them on your main page, but yep, should be there. Connecting your wallet to OpenSea doesn't have anything to do with the hack. The OpenSea exploit is related to listings. So if you put something up for sale on OpenSea, that, and especially on the new contract, because they just like deployed new contracts, they were migrating from V1 to V2 of their contracts, and people who put things up for sale on the V2 contract were affected by the exploit. But connecting your wallet has no problems. Like connecting your wallet doesn't do anything other than give them your address, public address. So don't worry about that. And yeah, it's trending because like they lost hundreds of millions of dollars. Like people lost hundreds of millions of dollars because of the bug in their V2 contract. Security audits are important. Testing is important. Smart contracts are immutable. Um, but okay. All right. I guess without further ado, let's get started. Um, cool. So I'm gonna open up Remix. How much did we cover on Friday? Let's see. So where were we at? Oh no, where is my advanced solidity dot sol? Oh shit. Da, da, da. Great. Remix just decided to delete it. Oh, I did make a gist though, so that's nice. Advanced solidity dot sol. Alright, I'm just gonna copy paste everything we did the other day. Advanced Solidity.sol. All right. Oh, what? God, this theme is terrible. I can't even see that there's something here. It's gonna move it to like default theme. Okay. All right, and then I'm gonna make sure I am on Rinkeby or something, not on mainnet. Move to Rinkeby. All right. So, these NFTs will be dropped in batches. So we'll do a drop once every month. So if you were to graduate today or tomorrow or something, you will get yours next month. We'll do it once every month, most likely. But yes. All right. So last time we did mappings, memory versus storage locations, enums, structs, view and pure functions, modifiers, and constructors. Today, we're going to do events, inheritance, how to transfer ETH, calling external smart contracts, imports, and Solidity libraries. All right, so let us start with, let's leave events for later, because we're going to go in depth, and events are a long topic, so I want to breeze through the easier ones first. All right, let's start from inheritance. Okay. So, inheritance. I'm gonna make a new contract. Inheritance. Actually, I'm gonna name it like inheritance A. All right, and you'll see why. So, first of all, what is inheritance? So if you're coming from, if you have background in any object-oriented programming language, this may sound familiar. Inheritance is the way that one contract can inherit, like take, all the attributes, is like variables and methods, which are functions, of any other contract. So if you're coming from an object-oriented programming background and C, is this better now? Is my sound better now? I increased the volume, but if I increase it too much, there's going to be static. So hopefully this is fine. But okay, so if you're coming from an object-oriented programming background, if you've worked with languages like C, C++, Java, even Python and JavaScript actually, and you've worked with classes, if you worked with classes, there's this common example. When you're learning classes for the first time, there's this common example of like, oh, class animal, like, I'll just actually open it up. So if you're learning classes in any programming language, let's look at JavaScript. There is a common example of animal and dog and cat. So this one is super basic. Let's do JS classes inheritance actually. Okay. Oh yeah. Okay. So yeah, there's like this common example. I guess this one is also fine. So you have a class, you have a parent class called car in this case, and then you have a class called model, which is an extension of the car class. So the car class by itself only has a car name, and it has a function called present where it says I have a this.car name. And then we have another class called model, which extends car, and it overwrites the constructor, and then it has different functions. But basically, you use inheritance to sort of like extend the functionality of one thing or the other. We kind of used it without really going too much in detail when we were in the freshman track and we were building NFTs and we were building tokens. We were doing contract LW3 token is ERC20. So we didn't really go into detail about that, but when you did is ERC20, you were actually like inheriting everything from the ERC20 contract, right? That's an example of like simple inheritance. So in Solidity, we perform inheritance using the is keyword. So we say like contract A is B. And we do this in freshman cryptocurrency and NFT levels. All right. Additionally, other cool things about inheritances. First of all, Solidity supports multiple inheritance. What that means is you can inherit from more than one contract at a time. You can like inherit from like 5 different contracts if you wanted to. So, and we will look at an example. So first of all, Solidity supports multiple inheritance where your contract can inherit from more than one other contract. All right. So this is the first thing. Second thing is that sometimes your parent's contract may have a function, but you don't want to use that. You want to sort of override it and you want to apply your own custom logic on that function, right? So you can do that. And again, we will look at an example for this, but a child, so when you're doing inheritance, the terminology is there's a parent and there's a child, right? So the contract you're inheriting from is the parent and your contract is the child. So a child contract can override a parent contract's function using the override keyword in Solidity. But only functions marked as virtual, and again, this will seem very familiar if any of you have C or C++ background. Functions that are marked as virtual are the only ones that can be overridden. Other functions cannot be overridden by the child. And we will look at examples, so don't worry. And last but not least, order of inheritance matters. So if we're inheriting from 2 contracts, it matters which one you say you're inheriting from first and which one you're inheriting from second. And we will see again why it matters and exactly what difference does it make. All right. So to show off inheritance, I'm going to create a bunch of different contracts. All right. And I'll show like inheriting from each other and so on. So it might be easier if I do this in a separate file, so this one doesn't get like polluted. So I'm going to just create a new file just for inheritance. I'm going to name it inheritance.sol. Just give it a pragma solidity of 0.8.4. All right. So we're going to create 5 contracts, A, B, C, D, and E. So contract A, then we're going to have a contract B, contract C, contract D, and contract E. All right. So we are gonna, what we're gonna do, we're gonna declare a function in each one of them, and we will demonstrate everything I just mentioned here. Oh God, dude, I hate remix sometimes. All right, refresh. All right. Wait, just Remix just decide to get rid of all my code? Like, seriously? All the comments I just wrote, they're gone. That is just beautiful. See, guys, this is exactly why we don't use Remix. That's why we use Hardhat, because Remix is a buggy piece of software sometimes. And it just decided to get rid of all my code. So all the comments I wrote about inheritance are no longer here. And that is annoying. That is very annoying. Okay. All right. So, well, I had listed down 4 things that inheritance has. 1, Solidity supports multiple inheritance. 2, functions marked as virtual in parent contracts can be overridden by child contracts. 3, child contracts can override parent functions using the override keyword. And 4, order of inheritance matters. So we will see how all of these things happen. We'll see how all of these things happen in here. All right, so what we're going to do, we're going to create a function in each one of these contracts. And some of them are going to override the other ones. Some of them are just going to use their inherited values. Let's just see. All right, so let's say contract A is the top level parent contract. A will not inherit from anything. All right, and let's define a function called foo. Foo is a pure function, and we will mark it virtual because we want the children to be able to override this. We will mark it virtual, and it just returns a string, and it will just return contract A. All right. So when we call this function, we will know, like if this specific function is the one that gets run, we will know it's coming from contract A. All right. Virtual marks this function to be able to be overridden by children. All right. So this is all A is. We'll leave A here. Then we'll do contract B, and we're gonna inherit A. All right. So we'll say contract B is A. So B inherits A. And then what we will do is we will override a.foo. All right. So we will override the foo function in A. And so we can do this by like writing a function with the same name, and we will say public pure, and we will say override, and we will say that this also returns a string memory, and this will return contract B. All right. So at this point, let's oh god, Remix is stuck again, guys. Remix is not responding. If I exit it, I am scared it will delete all my code again. Well, I guess I can't really do anything. All right. That is just beautiful. Of course, it deleted all my code. Amazing. All right. I'm gonna write code in VS Code, and then I will copy paste to Remix when I want to demonstrate, when I want to deploy it and actually demonstrate things to you. All right. So let's get VS Code open. I'm going to close Remix for now. And let's just create a new file. Actually, let's create a new folder somewhere. All right, we're gonna write code in VS Code. Keeps deleting it. All right, inheritance.sol. Go back here. Close all random windows if that's what's lagging my PC. Close Spotify. Close Notion. Close everything I don't need right now. All right, so let's zoom in. And let's start once again. So Pragma Solidity, 0.8.4. We had 5 contracts. Contract A, contract B, contract C, contract D, and contract E. And once again, real quick, multiple inheritance. These comments keep getting shorter every time I have to rewrite them. Multiple inheritance, virtual keyword to mark a function as being able to be overridden. Override keyword to actually override a function. And then order of inheritance matters. All right, so let's start again. So I had a function here called foo, and I had defined it as a public pure virtual function that returns a string memory, and this was just returning contract A. All right, so that was fine, and then we did B inherits A, and we did B is A, and we did function foo public pure, public pure override returns string memory, and this would return contract B. All right, so we were here. All right, so what this means is, like, when we call foo on contract B, it will return the string contract B because we overrode A, right? Had we not had this function here, if I just got deleted, if I just deleted it, the function would still exist on B, but because it would exist because of the fact that it's coming from A. All right, and in that case, if I call b.foo, it would return contract A instead of contract B. It returns contract B because I'm overriding that function. All right, so close YouTube, close everything. My laptop is being slightly laggy. All right, so yeah, does that make sense that it will return contract B if I call it right now, call the foo function, but if I call foo and delete this, it would return contract A. All right, so let's try remix once again because I do want to show this to you. I do want to be able to show this to you guys. So let's take all of this. Oh, my code is magically back. What the hell? Wow, that's absolutely beautiful. All right, guys. Okay, so, well, we have this code. I'm gonna compile this. What is going on today? It looks like it's hung again. Yep, it's gone. I don't think it liked that it gave me my code back. Yeah, it's okay. Start from empty. Compile. Please work. Is it just me? Like, is Remix working fine for you guys? Is it just me? Did I just restart my browser? All right. Okay, so you have this code. Go here, compile. Oh, it worked. Thank God it worked. Okay, it compiled. I'm gonna deploy this. And let's just use JavaScript VM, okay, just because it's faster. So I'm going to deploy. I'm going to deploy contract B, right? And then if I call foo, it's going to return me contract B because we overrode it. But if I commented this function out and I compile it and I deploy it again, if I call foo now, it says contract A, right? Because the function is coming from A now and we didn't override it, so it's returning contract A. So this is how you override functions. But what if, this will get a little more interesting, what if we wanted another layer of inheritance here? What I mean by that is, what if we want that our contract C, actually, you know what, let's leave B here and let's do contract C is A. So we will C inherits A as well. But the difference will be this time. So we have mostly the same thing. So it overrides the foo function. And it returns contract C. But we will make one slight difference. And that difference will be, we are going to say that C itself, this itself here, will be a virtual function. So we're going to say both. We're going to say it's virtual and it's also overriding. So what this means is I'm overriding the function from A. So when you call it, it will return contract C. But at the same time, I'm marking it virtual. So if any other contract inherits C later on, they can override it further, right? Because if a contract inherits B, the foo function is not virtual. You cannot override it if you're inheriting from B instead of A. So by marking it virtual, you're saying I'm doing an override, but at the same time, I'm making this function itself able to be overridden in the future, right? And we're actually going to do this with both B and C. We're going to make both virtual and override functions, and both virtual and override means override a.foo, but also make c.foo able to be overridden later if someone is inheriting C directly. All right. Okay. So this is what we mean by, like, we're going to have both virtual and override. Both virtual and override. And this is cool because then you can do, like, things like you can create an extension of a contract which has their own custom logic, but then maybe people want to extend that further out and add their own logic on top. So you can have like a super long chain of virtual and overrides, and like goes deep in inheritance. So A goes B, B goes C, C goes D, and they all override each other and borrow each other's functionality a little bit. All right, so we see multiple. Okay, we haven't seen multiple inheritance yet. We've seen virtual and override. So let's check out multiple inheritance, and this will also show you why order matters. All right. So let's have contract D inherit. D inherits from both B and C. All right. So we'll say contract D is B, and it's also C. And straight up, it's giving me an error. It is saying that both parent contracts, derived contract must override the function foo because two or more base classes define the function with the same name and parameters. So the problem is both B and C have a function called foo. They look the exact same. So when I'm inheriting from both, it doesn't know which one to use. So it is confused what happens. And now what we can do is like, yes, we can override them further, and we can do public pure override string memory. And this, it's still not happy with this. All right, it's still giving us an error. It's saying function needs to specify the overridden contracts. Because we're not overriding a single function. This function exists in both B and C. So we need to tell it, and like when we say just override, this worked fine here because we were only overriding a single function that was coming from A. We were doing single inheritance. But now we're inheriting from two contracts. They both have the same function but return different things. And when we say we want to override it, it doesn't know, do you want to override the one from B or do you want to override the one from C? All right. So we have to actually explicitly tell it that I want to override both versions, both B and C. I want to override both of them. And then what we can do is there is a special keyword called super. You might have seen super in JavaScript. I believe it also exists in C++, but I'm not 100% sure. Super is a special keyword that lets you call your parents' functions. All right. So what I can do here is, instead of overriding it myself, just to demonstrate you multiple inheritance, I can just say return super.foo. And this will call the foo function in the parent. Now here's a question for you guys. Foo, we have two parents. They both have a function called foo. What is going to be returned? Contract B or contract C? This will relate to why order of inheritance matters. What do you think will return here? So you're saying it will return B. Well, it can't return both. It can only return a single string. So you can't have both the strings being returned. And you're saying B, maybe because B is the first one. But actually, no. The order of inheritance goes left to right. So let me, actually, you know what? I'm going to deploy this. I'm going to use Remix. Hopefully it works. And I'm going to show it to you what happens. And then we can reason about it. So compile this thing, deploy contract D, deploy it. And then if I call foo, it's saying C. It's saying it's coming from contract C. And the reason it's coming from contract C is because C is the rightmost contract with that function defined. So you can think of it like B had a function, and then we inherited C afterwards, so C's function takes precedence. It's like, oh, I came later, I have the same function, we're going to use mine instead of yours. And then when you call super.foo, it calls the function from C. And this is why order matters. if I had inherited in the order of C comma B here, it would have given me contract B instead. And we can actually see that. So in contract E, I'm going to do, it inherits from C comma B instead of B comma C. And here we're going to have a function foo. Again, public pure override, and we need to tell it we're overriding it in both, and returns string memory. And here, if I do return super.foo, this will actually give us contract B, because that is the rightmost contract with that function defined in it. So I'm going to copy paste this here, delete the old one, and deploy contract E. And if I call foo, it says contract B. So this is an example of multiple inheritance, and it shows you why order matters. One common question that I didn't explicitly touch is, why would you want to use super? If you're calling the parent function anyway, why are you overriding it in the first place? What's the advantage of overriding if you're going to call the parent function anyway? So one common reason why you would actually want to do this is if you just want to add some additional, like security checks to the function call. So let's say you wanted to add a single line here, which would be like, oh, I want to require some statement. I'm just going to say true. Otherwise, give it like an error of some kind. So you just want to make sure that this statement is being run, but if this is true, then you can go on and do the rest of the function call. All right. In fact, in our NFT drop earlier today, we actually did this, and I can actually show it to you right now. So if we look at the contract for the NFT collection we just dropped today, let me see, where is Polygon scan? All right, so this is our contract for the NFTs we just deployed today. If I look at the code for this contract, we have a function here. So one thing we wanted to do in this function, in this NFTs, is that we don't want you to be able to sell them. We don't want you to be able to transfer them because they're meant as a proof of your graduation, and we don't want you to just hand it out to other people because they weren't the ones who graduated. It was you who graduated. So these NFTs are actually non-transferable, and the way we did that is the ERC 1155 standard we use has a function called safe transfer from. We overrode that function, so we did function safe transfer from public virtual override, so we overrode that function, and the only thing we added was we added a modifier. And this modifier basically says, unless you're one of the team members, because we had to send it to you, obviously we had to transfer the NFT to you, so unless you're one of the team members, you cannot transfer this NFT. And that modifier is a simple modifier. It just says that require that this address is part of the whitelist, otherwise throw an error unauthorized. So we just added that modifier, and then we were like, if this is okay, then we can just call super.safeTransferFrom. So that's why like super is useful. We didn't have to like copy paste all the code that was in here. We just did super.safeTransferFrom, and the only thing we added was this check that only team members can transfer this NFT. So hopefully that makes some sense. And order of inheritance makes sense. So C is the nearest parent in this case. I don't know about the word nearest, but you can think of it, it's like, it's the latest contract which had that function specified in it. The latest contract with that function is the one that gets called. So in this case, in D, C was the latest contract, so it said contract C. But in E, B was the latest contract, so it said contract B. And I mean, you can force it to use a specific version if you want. You can like force it to be like return c.foo, and you don't have to like say super. This way you can get it to return c.foo. But like, I'm just saying, what happens if you return super? In super, order would matter. We don't allow airdrops. If you already have a freshman graduate NFT, you're not going to get another one. You can log into the website with a new email and link your same ETH address. You're not going to get another one. We have that check in the contract that if you already have it, the transaction will fail. It will not be sent to you. You can only have one of each graduate NFT. Okay, so this was inheritance. I'm going to move this into Remix. I'll share a GitHub gist of it later. So Advanced Solidity is gone. Copy the GitHub gist. Thank God I made the GitHub gist. Whoever asked me for it that day, you actually like just saved this entire session from just getting rid of everything. I'm just gonna copy paste all of this here. All right, so we've done inheritance. I'm gonna move events till the end. So now we're gonna look at how do you transfer ETH from a smart contract. All right. So let's create a new contract here. Contract ETH sender. All right. So obviously, if you're a user, if I wanted to send you ETH, I could just go into MetaMask and I could just go into MetaMask and I could just like send it to you, right? Like I have a certain balance, I can just click send and put in any address and send it to you. The contracts don't work the same way. Contracts don't have a wallet. I mean, in this sense of the word wallet. And you need to write code to send ETH from a contract. There are 3 different ways you can send ETH from a contract. 3 different ways to send ETH from a contract. And reason for having 3 different methods is basically Solidity got upgraded over the years, and shitty code got deprecated. So 2 of the 3 methods are no longer recommended to use, but they still work because like you cannot have Solidity. A past feature of Solidity cannot be made to like stop working, because any contract that was deployed at that point in time, you can't just make it stop working. So they have to support every single feature they've come out with, even if they know that it's shitty. So 2 of the 3 methods to send ETH from contracts actually are no longer recommended. So I'm not going to teach you those. What is recommended is the call method, and that's what we're going to look at. So to do that, let's say we have a function. We have a simple function called mirror. Yeah, let's just call it mirror. All right, and it is a payable function, and all it's gonna do, mirror takes in some ETH and sends it back to the person. It doesn't do anything. You send it some ETH and it sends it back to you. All right, just to demonstrate how transferring ETH works. Obviously, it's a pretty useless function, but you send it some ETH and it'll send it back to you. All right. So what I'm gonna say is, so we have like message.sender is the person we are getting the ETH from, and also the person we send it back to. Then message.value is the amount of ETH we receive and amount we send back. So that is fine. Let me put my phone on silent. All right. So what is important is how do you actually do this? All right. So you have, first of all, you need to create a payable address. So you do like address payable target. So regular addresses in Solidity, you cannot send them ETH. You need to mark them with this special payable keyword. Same thing as functions, which are marked as payable, which means they can receive ETH. And payable targets, like payable addresses, means like they can receive ETH, which means you can send them ETH. So you do address payable target, and you wrap payable and message.sender. So you mark message.sender as a payable address. And then just for readability purposes, we'll just say UN256 amount is equal to just message.value, just for readability. So the way it works is, what we can do, there is a function called, like it's defined on addresses. So on any payable address, you have a function called call, and call, you can specify some arguments, and then you call it like a function. All right, and you can like send some data along, but we don't want to send any data along. We'll just pass an empty string, and in here in the arguments you can specify a bunch of different things. One of which is the value, which is the amount of ETH you want to send it. So it's going to look like this, and call returns two variables. So far in Solidity, we've written functions that return a single thing, but actually you can return multiple things from a function. So you can, like, for example, you can have a function that returns 2 uints, or 1 uint and a string, or like 5 things, right? You can return as many things as you want from a single function. You're not limited to just returning a single value. And call actually returns 2 things. The first is a boolean indicating success or failure. The second is some bytes, which have data. And this thing, it only returns data if you send it some data. All right. So if you send it some data, maybe it has a response back. You don't need to worry about that right now. That's really used for if you're calling other smart contracts using this. Usually you won't do that. We don't have to worry about that right now. We'll get into it in the calling external contract section. So let's just say it has a second possible value, which is data, but we don't need to worry about it right now. The thing we're interested in is the first value, success or failure. Let me look at chat. Is there a good way to debug contracts? I mean, write a lot of tests. Don't rely on manual testing and manual debugging. Write a lot of tests. Use something like Hardhat and write a bunch of tests for your contract. And if your contract is going to be dealing with money, hire a professional security team to audit the contract for you. And that will cost a lot of money, but that's what you have to do if you expect your contract to be dealing with lots of money. If it's your own thing, then debugging, like, write tests. If it's just like a side project, like write some tests, use Hardhat, do console.logs, do manual testing. Yeah, like that's basically, it's the same as like debugging in any other language, really. Like, if you're using Hardhat, you can do console.logs, and then you call functions yourself, and you see, like, is it working as expected? Are there any errors? And then over time, you refine your contract more and more. You fix bugs and you fix features until you're happy with it. It's the same as like coding in any other language, really. But yeah, so when we do call, it returns two things, as I said. The way you accept two things from a function, like usually if you had a function that returned a uint, if you had a function that returned a single uint, you can do something like uint result equals some function, right? But in this case, we are getting two things back, and the way you do that in Solidity is place some some parentheses, and you do bool success, and then you do bytes memory data, and this is equal to target dot call, and we give it a value of amount, and we call it with no data. And this is how you accept multiple return values from a function. Additionally, since we are, and let's say that in this case we just we required that it succeeded. So require success equals true, or we can just do require success because it's a boolean, and otherwise we say failure. So this is fine. This thing is going to give us a warning that it's an unused variable, which is where we don't care about that value. So what you can actually do is, if you want to ignore a parameter that's being returned by the function, if you want to, like, for example, in this case, ignore the second thing, just delete it. All right. Keep the comma. You have to keep the comma. If you delete the comma, it's going to say that this function returns two values. You're only taking in one. This is wrong. Keep the comma, but don't write anything after it. And that's the same thing as saying, like, ignore the second value. I don't care about it. And hypothetically, if you wanted to ignore both the values, you just do this, and all you have is a comma. Oh, that didn't work. Expected primary expression. Oh, I guess you can just not care about return values at all in that case. Yeah, sorry. But yeah, you do this, and this means ignore the second return value. I don't care for it. So let us take this into Remix, our friendly friend Remix. Place this here. And this I'm gonna do this on Rinkeby, so you can see the transactions going back and forth. I'm gonna switch to, oh god, please work. Alright, it's dead. Alright, so Advanced Solidity. I think this code might be getting too much for Remix. I'm just gonna take this last part. I'm just gonna take contract each sender. Just add pragma solidity 0.8.4. Alright. Let's see if it compiles. I wish there was a better tool than Remix to do this. Nope, it's dead. Okay. I guess I'm gonna restart my browser again. Alright. And take this code, paste this here, and to compile, try to compile this file. It's hung again. Okay. Yep. Yep, I know how to do this. All right. Let's do eth sender.sol. We'll do pragma solidity 1.8.4 and copy over this thing, this contract. All right. So, okay, here it worked. Okay, perfect. All right. So compiled. Unfortunately, I can't do it on Rinkeby because I opened incognito and I don't have MetaMask here. I'll do it on JavaScript VM. So on Remix, I'm going to deploy this. And read functions on Remix means it's a payable function. And the way you specify value, like how much ETH you want to send along with this payable function, is you specify a value here on Remix. When you're writing your own code, when you're writing in like JavaScript and calling functions on your website, you have to specify the value as part of the function call, and it opens up the MetaMask. Here, you have to specify the value here, and then it would open up the MetaMask to authorize that transaction. Since we're using JavaScript VM, it won't open up MetaMask, but I'm just going to say I want to send like 1 ETH. And notice that my account currently has 99.99999 ETH. All right. It's because, actually, yes, let's use this account, which has a flat 100 Ether. So on the JavaScript VM, you get a bunch of accounts for free, which are all preloaded with 100 ETH. So I'm going to send 1 ETH to this mirror function, and I call that. It sends us 1 ETH back, but you lose some in gas. So like a tiny amount of Ether got removed because we had to pay gas, but it came back to us, right? It was able to send it back to us. Like if I got rid of these 2 lines here, and deploy it, like in that case, I'm just sending it ETH and not getting anything back. And in that case, it just goes down to 98. But it was able to send that money back to us, so all that got removed from my account was a tiny bit of gas cost. Which makes sense, right? So again, I do this, and it just like reduces my balance a little bit at the very end. But this is how you send ETH to people. So recapping, mark an address as payable, do payable address.call, give it a certain value, which is the amount of ETH you want to send, and then it will return you a Boolean saying, did it succeed or did it fail? So yeah, that's how you send ETH from a smart contract to somebody else. And again, there are 2 other ways that you can send it. I didn't teach those 2 other ways because they are deprecated and no longer recommended. But if you want, you can look at them on your own time, but they are not suggested to use. All right, so moving forward. We did how to transfer ETH. Let's take a look at, let's do the easy things first. Let's do import statements and Solidity libraries. All right, import statements. I'm going to create a new file for this. So import statements.sol. Market pragma solidity 0.8.4. Import statements, I mean, we've been using it in Freshman all over the place. Essentially, there are 2 kinds of imports you can do. One, it's a local import, so you're importing your own Solidity file, or 2, it is a like remote import, which means you're importing it from a GitHub URL or something, or I guess you could call it like external import. So local imports kind of work like, like I can just do, for example, import./inheritance.sol, because we created this file. So I can import this locally like this, and then I can do something with it. So yeah, like that is one way to do it. The other way is I can import something directly off GitHub. So we do this in the freshman track. In the freshman track, when we do the cryptocurrency tutorial and the NFT tutorial, let me show it to you. So in the freshman track, when we, for example, when we do the cryptocurrency tutorial, we do an import like this, and we are importing directly from GitHub. And this is an example of an external import where you're just loading a Solidity file from a URL, and you can access all the code that's present inside of it. So the first one is a local import, and the second one, you can do this, and this will load the ERC20 file at that GitHub repo. Yeah, that is fine. This is just an extension error, but the code is fine. So these are the two kinds of imports you can do. I don't think this is a very complicated topic. The only one thing I want to clarify is when using Hardhat, we use OpenZeppelin contracts sometimes. If you guys have done the sophomore level, some of them, or the freshman, freshman we don't use Hardhat that much. But if you do the sophomore levels, you will see when we're using Hardhat, we use these OpenZeppelin contracts, but we don't import them externally. We actually download it as a package. We download OpenZeppelin contracts as a node package through npm, doing something like npm install at OpenZeppelin/contracts or something. And is this a local import or an external import? When we do something like import OpenZeppelin/contract/token/ERC20/ERC20.sol. Is this a local import or is this an external import? Well, I guess I kind of actually gave away the answer. I said this. So, so I guess I gave away the answer. So technically, this is not an external import, because when you download npm packages, they go into your node modules folder, and you're just importing files from the node modules folder. So this is still a local import, not an external import. External imports need to be from actual links, like something like this. Both this as well as this kind of import, these are both local imports, but this one, which is actually loading from github.com/whatever, this is an external import. So that's imports. Fairly simple. All right. Cool. Good progress. All right. Now let's look at Solidity libraries. Solidity libraries are cool. All right. So let's do libraries dot. So actually, let's just do it in Advanced Solidity. So let's say we have a contract. Like I'm gonna name it libraries. So far, we have written Solidity in a way where a contract was the only thing we were writing. And some of you who have done a couple of the sophomore levels, you may have also seen us writing interfaces. Some interface. So far we have seen like, I guess I should write it here. So far, we have seen 2 top-level constructs in Solidity. One is contract, and 2 is an interface. If you haven't seen interface, don't worry, you will see that in the sophomore levels and the programming levels once you get there. So we have seen these 2. There's actually a third kind, and it is called, there's actually a third top-level construct, and it is called a library. All right, what is a library? What is a Solidity library? So think about like libraries in any other programming language, right? Like npm packages, whatever. Actually, they're probably not good analogies, but I mean, a Solidity library is it is something that is typically used to add some helper functions to your contracts, and their limitation is they cannot contain any state. So this means you cannot have any state variables, you cannot have any mappings, arrays, structs, whatever, structs, etc. All you can do is have some functions that take some input and return some output. So you cannot maintain any state. It's just helper functions. All right. A very common library before Solidity 0.8, a very common library that was used was called SafeMath, which used to ensure all mathematical operations were valid, and there was no integer underflow or overflow going on. Solidity 0.8 actually comes with SafeMath built in, so we don't use it anymore, but it is a good example of what a Solidity library is. So we will try to recreate a basic version of SafeMath, actually just one function, which is addition. So let's see how we can do this. So first of all, we can define something. We can do library and SafeMath like this. So instead of contract, we say library, and you can have a function on it, say function add, and it takes in 2 things, so a uint x and a uint y. We'll mark it internal and pure, and it returns a uint. So all functions in libraries are actually pure functions, because libraries cannot have state, right? So they're only taking an input and giving some output. So pretty much all functions in a library are always pure functions. So all that we want to do is we want to try to add them, and we want to make sure an overflow did not occur. And you can do this by adding a quick statement saying ensure that z is greater than or equal to x, otherwise we give an error saying overflow happened, and then we return the value of z. So we have this SafeMath function which will fail if addition causes an overflow, otherwise it will return the value of z as usual. And then in our contracts, what we can do is we can use these libraries. So we can do we can have like a function called test addition, which takes in 2 things, and this is a public function, also returns a uint. And here, instead of returning x plus y, we can do return SafeMath.add x comma y. So this will call the function of the library. Yep. So that is Solidity libraries. They are basically things you do use to add helper functions to our contracts. All functions in a library are pure. Libraries cannot maintain any state variables. They can only have functions which take input and give some output. And a very common library that was used before Solidity 0.8 came out was Sophmore, because Solidity did not have overflow and underflow checks. Cool. Okay, so that is libraries. Are there any questions about libraries? I feel like it should be fine, hopefully. But yeah, if you have any questions, like, feel free to ask, of course. We will look at calling external smart contracts. Real world use case of Sophmore, like, overflows are super important. Like, you have to take care of integer. Are you familiar with like what integer underflows and overflows are? So basically, so you know how, like, let's look at a smaller example, something other than a UN 256. So integer overflow example. So imagine you have a uint8. It can hold values from 0 to 2 to the power 8 minus 1, which means 0 to, what is 2 to the power of 8? 2 to the power of 8 is 256, and minus 1, so it can hold values from 0 to 255. All right? Now, imagine you have a variable, which is like uint8 a equals 254. And then you have a variable b, which is like 5. And then you try to do uint8 c equals a plus b. So a plus b is 259, but a uint8 cannot store the value 259. So here, this is what causes an integer overflow. And overflow basically means that it exceeds the maximum possible value, so it's going to circle back at the beginning. So like, let's like look at what happens. So as far as EVM is concerned, since and this happens in like all programming languages, like Solidity is not special. Every programming language is susceptible to integer overflows and underflows. So like 254 plus 5 is 259. So C can represent up to 255, and then there's 4 units it cannot represent. So once it reaches the maximum value of 255, it will circle back to 0, and it will become 4. So the value of C after this statement would actually be 4, but you expected it to be 259. And the reason is it cannot hold the value 259, so it goes back to the start and adds 4 there. Again, this is all like pre-Solidity 0.8, because now these checks are built in. But in older versions of Solidity, this would happen. And when you're building financial applications, especially like DeFi protocols, you really need to ensure that your math is correct and that your math is sound. If your math leads to overflows or underflows, it can lead to all sorts of wacky behavior. People could use it to exploit your functions somehow, steal money from your contract, whatever. You want to ensure your math is proper. And to do that, in the past, people used the Sophmore library. And what Sophmore is actually doing is, like, imagine we passed the values x equals 254 and y equals 5 here. After this statement would run, z would equal 4 because of overflow. But then we have this require statement that after the addition, we want to make sure that z is still greater than x. And in fact, like, if you want to make it stronger, you should actually do z is also greater than y. And if it is greater than both of them, like that means overflow did not happen. Because the only way it is greater than 254 is if the value was 259. But because it wrapped and because overflow happened and it became 4, then this statement would fail and your transaction would fail. So this used to be a use case for like safe math. So overflow happens when you're adding value beyond the maximum range, and underflow happens when you're subtracting values which go beyond the minimum range. So like if you have like a equals 5, but then you do a minus b where b is like 10, so -5, and uints cannot hold negative numbers, so they would like wrap to the end and it would become like 250 or something. So DeFi apps where math is critical and your math formulas need to be correct, that's where safe math used to be used a lot. But now it is built into Solidity. But this is just an example of how you can use libraries. And the actual safe math library has like way more than just addition, obviously. So like if you Google for safemath.sol, it's by OpenZeppelin, and it has addition, subtraction, multiplication, division, modulus. It has all of those functions, and people would use this instead of using the regular plus minus operators. They would use the library functions instead. Anyway, that's libraries. That's safe math for you. All right, let's look at calling external smart contracts. So, the contract external caller. All right, so external smart contracts. All right, so again, like if you've done Sophomore, you've probably seen this already, but for people who haven't, I'm gonna explain it again. So contracts can call other contracts by calling functions regularly on an instance of the other contract. This is a loaded statement, but basically, if you are contract B and you want to call contract A, you want to call the function foo on contract A, you can basically do a.foo, but to do this, you need an interface for A, and we will get into what interfaces are. So what is an interface? An interface is kind of like an ABI that we have been using all across. So an ABI to a contract, it defines function declarations. So basically, what is the name of the function present in this contract? What are the input values? What is the return value? What is the visibility? So like, is it public, private, external, whatever? And what is the mutability? So is it view, is it pure, or is it none of those? So an interface is basically just the name of your function. And if you're calling an external contract, Solidity needs to know what exactly is this function that I'm calling. Because if you think about it, what goes on in the Ethereum virtual machine when you're calling contracts, the Ethereum virtual machine doesn't deal with like strings, right? Like this is still human readable code. They don't send like strings back and forth. They send like bytes, right? They talk in binary. The Ethereum virtual machine, like just to optimize for space and for being able to send minimal data across the wire, they talk in binary. And that means every time a function is called, you need to convert the human readable function name and the function parameters and everything into bytes, send it off, and then when you get a return value back, you need to decode those bytes back into something that is human readable. When you're building websites in JavaScript and you call functions on your contracts, helper libraries such as ethers.js or web3.js do this for us. So ethers.js, under the hood, when you call a function on a contract using ethers.js, it would convert it into bytes, send it to the network, and when it gets a return value back, it would decode those bytes back into something like the developer can use, and it's human readable. Similarly, an interface, and ethers.js does this based on the ABI, right? We give it an ABI, and the ABI tells it what functions exist, what are their names, what are their input values, what are they, like, it answers the same questions as an interface. In fact, the I in ABI stands for interface. So even in Solidity now, if you're calling a different contract, you need an interface to that contract. And an example of this is like, let's say you want to call an ERC20 contract to check the balance of a certain user. All right. So let's say we have a function called do I have balance? And this is a public function. And let's say this function also has a constructor. So here we specify the address of some ERC20 contract, and we maintain like, actually don't worry about that right now. So in do I have balance, we want to do two things. So first, check if message.sender owns any ERC20 tokens from ERC20 contract, and two, require that the balance is greater than 0, otherwise fail the transaction. All right, and again, this contract external caller is not the ERC20. It's a separate ERC20 that somebody else or maybe you deployed in the past, and we want to call the function there. So ERC20 contracts have a function called balance off, and if you want to call it, we first need to create an interface. So we'll create an interface, call it minimal ERC20, and the reason we call it minimal is because we just need to include function definitions for the functions we care about. We don't need an interface for the entire contract if we are not using those functions. So since we are only interested in one function, that is balance off, we are fine with just writing the interface for that one function. We don't care about the other things. So we'll say that ERC20 contracts have a function called balance off that take an account address, and that are view functions that return a uint256. And this is the only function we want to use. So now in our external caller, we can have a state variable of the type minimal ERC20, and we can name it external contract, and in our constructor we can set it to the address. So we can say external contract is actually equal to a minimal ERC20 on this address we passed it in the constructor. Or I mean, if you know this address beforehand, you can just do this here. You can just do ERC20 and then have like 0x86, whatever the address is. But we'll let the user enter it. And then once we have this interface, do I have balance, we can do something like uint balance equals external contract, which is our state variable, external contract dot balance up. So it recognizes it because this is the only function we wrote in our interface. We do dot balance off and message dot sender. And then we just have a require statement which says balance greater than 0, otherwise you're poor. you don't have enough tokens. Right? Does that make sense? And yes, this can be restricted as a view function because we're not changing state. Does that make sense? Sorry, I was replying to someone. All right. Okay, sorry about that. Okay, so all right, so interfaces are fine. And again, like if you want to call a different function, perhaps like you want to look at the name of the contract. Let's see, what does ERC20 look like? So like the actual ERC20 contract has all of these functions. So let's say we want to fetch the name. I can take this. I can put it in my interface. Leave it like this. I don't need virtual and override here because this is just a definition. And you can mark this external. Okay. And then like I can have another function called get ERC20 name public view, and this just returns external contract dot name. Right, and you can like do whatever functions you want. Different number of arguments and return statement. Oh, right. Returns string memory. All right. You can call whatever functions you want on the ERC20, and if you give it a random address, if you give it an address that's not actually an ERC20 and that doesn't have these functions defined, it will just give you an error when you try to call those functions, and your transaction, like, it will just fail, and it will just say that this address doesn't have this function defined on it. So assuming that the address you provide is an actual ERC20 contract, then these will work. Otherwise, it'll just say like this function isn't defined. All right. There is another way you can call contracts. So perhaps you want to call a contract for which you don't have the ABI. Like maybe you know like about the existence of a single function, but you don't know exactly like what it is. There is a lower level approach to call a function directly without needing to use an interface. And it kind of goes back to this dot call thing we did, where you can pass in some data while calling an address. I will not get into that right now because it is significantly lower level and it requires some like cryptography understanding. We may cover it in junior or senior. Don't worry about that right now. Anything we do in Sophomore, you will have the interface for it, and like, or at least like you can write the interface for it. So don't worry about the lower level calls just yet. And like, oh, what happens if I don't have the interface? You can still call them, but it's a little more tricky and a little more involved. It's not as easy as just doing like a dot function call. All right, last but not least, events. And this is going to be an interesting topic. All right, so what are events? Events are essentially logs on the Ethereum blockchain. This is very vague. You can use events to log information on the blockchain, kind of for a proof of history that something happened at a certain block. All right, and we'll look at an example. The way you define events, So, I mean, events have a name. Events have a name. They have arguments that you want to log, and that's basically it. So, like, you can think of it kind of like it's console log, like it's different from console log, but like in JavaScript you do console log and you like give it like a few things. So similarly, like events, they have a name and they have like a bunch of different arguments that you want to log on the blockchain. So the way you define events is like, let's create, it's like you use the keyword event, you give it a name. So it's like test function called, and you give it, like, let's say I want to give it an address and a message, right? And the way you use events is inside a function, like let's say I have a function called test, and all it does is it will emit an event. So events are emitted. You emit an event on chain. So you emit it, and you like emit test function called message.sender, and then you do like somebody called test. All right, this is how you define an event and then emit an event. I will get into a use case of it, but before I do that, I want to show it to you. So, God, please pray that remix works, because I want to show it to you on Etherscan. It is useless to see this just on JavaScript VM. So, pray to God. And never mind, it's hung already. All right, you know what? We'll just look at random contracts on Etherscan. Or actually, we can look at our NFT contract from earlier today. The graduate NFT contract. So if I look at Polygon Scan here, so when we minted, when we did a mint, so we are using the ERC 1155 contract, and the ERC 1155 contract has a few events that it defines. So they have, oh, it's not defined here. They define it in their interface. So we'll look at, so the ERC 1155, they have four different events that they define. One of them is this event called transfer single. So this event gets emitted every time a single NFT is moved from one address to the other. So this has a few different values. It says transfer single has an address of an operator. So the person, so this would be the same as the from address in most cases. And then there's a from, a to, a token ID, and a value, like how many NFTs do you transfer with that token ID. And if we look at our contract, So this function that we minted a NFT to some address, and a mint is essentially a transfer. You're transferring something from the null address from living in oblivion to an actual address. And now on Etherscan, you can go onto this logs tab here. And if I go into logs, it shows me that there was an event log that happened. And there was an event of the type transfer single, which had 1, 2, 3, 4, 5 values. And like it is able to decode some of the things automatically. So like the operator was this address, which is our address. The from address was the null address because it was a fresh mint. It was being minted for the first time, so it comes from null. The to address was this person's address, and then the ID was 0, and the value was 1. And in fact, you can actually go to a contract on Etherscan, and you can click on events. If you look at events, it is an entire log of all the events this contract has ever emitted, along with which block they got emitted in, how long ago was it, and like what were the values of those events. So yes, ABI is just for readability. You cannot exploit it. You use ABI just for like telling Ethers.js what functions exist and how to encode and decode data. But back to events. So this is a log. This is literally a log of all the actions this contract has taken in the past. So every single transfer that happened, you can view a log for how long ago did it happen, what were the values, blah, blah, blah. All right. Now, you may be wondering, like, why do we want to do this? All right. So think of it like this. Think of it like, imagine you had an NFT. All right. I'm just going to create like some fake stuff in here. So imagine you had like imagine this was a contract for a single NFT, and you had a function called transfer. It was a public function, and you had a variable called like address owner of NFT, and the transfer function would like require that if message.sender is equal to owner of NFT, otherwise you cannot transfer. And then if it is the owner of the NFT, maybe like he can send it to someone else. So essentially like change the owner to a new address, right? You can do owner of NFT equals new owner. So highly simplified thing where like something is changing hands, right? There is an initial owner, and then they can transfer it to new owners over time. Now imagine you wanted a website or something where you were like, I want to display the entire trading history of this item. I want to see from the beginning of time who was the first person who owned it, who did he sell it to, who was the second person who owned it, who was the third person who owned it, and so on. All right? If you wanted to do that, one approach would be you can have an array of addresses, right? You can have an array, and you can be like all owners, and then you can say that you want that message.sender. So you can check like address latest owner it's the last item in the array. So we can do all owners dot length -1. So access the last item of the array and ensure that message.sender is the latest owner. And if it is, then we do all owners dot push new owner. Okay. So this way you have access to the entire history of owners. The problem is this is very expensive. We are storing an array which can grow infinitely large, and the gas costs for doing this can be very expensive. Storage costs in Solidity are very expensive. This is where events come in, because this solution is not good. So what you could do is you can only store the current owner. So I'm going to undo all of these changes. You can store a single owner, and along with that, to rebuild the history, what you can do is you can create an event called like transfer, which has an address from, address to, all right? And then every time the item is transferred, you can emit a transfer event that says this thing was transferred from message.sender to new owner. And events are much cheaper, much cheaper gas cost. And in the future, on your website, what you can do is you can just look at the events of the contract, right? You can look at the events of the contract, and you have the entire history there. And you can say like, oh, like at this block, roughly like 2 hours ago, this thing changed hands. It went from this guy to that guy. And then like this happened, and this happened, and this happened. And then you can build a canonical view of things. And OpenSea actually does this. So if you go to OpenSea on like any random NFT collection, I'm just going to pick like some random NFT. Okay, please open up. All right, yeah. So on OpenSea, if you look at any NFT, you can see its entire history. So you can see like that. Oh, we don't want to look at offers. Let's just look at transfers. So like we see like 3 months ago, this thing was minted. It went from null address to this guy, and then 9 days ago, this guy sent it to this guy, and so on, right? So the way they build up this entire trading history is because they can look at events. So ERC 1155 has transfer events, and ERC 721, which is the other NFT standard, the main NFT standard, that thing also has transfer events. Yeah, so it has a transfer event that looks very much like what we did, except we didn't have a token ID. But yeah, ERC 721 has a transfer event. It's like from, to, and token ID. And it is emitted every single time an NFT changes hands. And then OpenSea can just look at all the events and figure out the entire trading history of this NFT. So they can look at all the events where the token ID was this token ID 8680, and then they can figure out the entire trading history for that thing. That is what events are used for. It's building a proof of history on chain without just building an infinite array in your storage. So you're just logging things on the blockchain, and then you can go through those logs to get like a proof of history of something. In Junior, we will look at ways to how you can read events and make it really simple. Because currently, like as you see, like these are all like hex data, it's in bytes, and it doesn't look nice. Reading events manually is a little challenging, and in Junior, thankfully, the Ethereum community has created a lot of tools and frameworks which make dealing with events very easy for the developer. And we will look at something called the graph in the Junior track, where we will actually be using a lot of events. And the graph is basically a very easy to use tool to read events from contracts. And you can create like your own, they call it a subgraph. So you can create your own subgraph, and you can easily read and look at the history of all the events on your contract for a certain thing. So that's what events are used for. Proof of history on chain without storing infinitely large arrays or whatever. You just emit an event every time something happens, something meaningful, and then you can go on later and look at all those events and have like a trading history of the NFT or whatever you may want to do with it. They're also really good for like Another example other than trading history is also really good for like things like I don't know, like if you're building a game, right? Like maybe you're building a game on the blockchain, and what you can do is like, let's say it's like a multiplayer game. So when a new game is started, you can emit an event like game started, something something something, and like your website can look at that event and your website can say, oh, there's a new game going on right now, click this button to join or whatever, right? And then people compete, people do whatever they want, and then at the end you have an event saying game ended, along with the address of the winner, right? So that way you don't have to store like huge arrays of who won what where. You just emit events, and your website can look at those events and see that, okay, 2 days ago we had a game that started at this time and it ended at this time, and this guy was the winner of that game. And you don't need to use like a huge amount of storage in your contract. You can just parse those events on chain. So events do get stored on the blockchain. I'm not saying they're not getting stored on the blockchain, but I'm saying they're not stored as part of your contract, right? Your contract has a certain amount of storage. So all the variables here, like this variable here, is part of your contract storage. And adding anything to contract storage is expensive. Events, however, are stored on the blockchain, but they're not stored as part of your contract storage. It's just like, there's just like an entirely separate storage for like event logs on Ethereum. So there's just like this huge list of events, and every single block new events get added to that list, and it's just like a separate place of storage that has nothing to do with your contract storage per se. It's just like a huge event log. It's like logging something to the terminal or logging something on the blockchain, and it's stored with the blockchain, but as like a separate part of storage. It's not related to your contract directly, and it's cheaper to do that. It's cheaper to do that compared to storing something in your contract storage. It costs less gas to emit an event versus adding something to an array. In Junior, once we start heavily using events, you will realize that events are also much easier to work with if you want anything to do with history or what happened in your contract in the past. Because so far, the apps we have made in Freshman and Sophomore, they only deal with what's going on right now. What is the current state of your contract? We don't have anything to do with what has happened in the past already, like what changes has the contract gone through. And when we start using events, we will see that there are a lot of cases where you would be interested in learning what happened in the past, not necessarily just what is it right now. And in that case, events are very, very useful, because, like, as I showed to you on OpenSea, like, trading history is very useful to see, like, how an NFT changed hands, and things like that. So, or like, when was a game started and when did it end or whatever. So there are a lot of use cases where you want to make use of what happened in the past, not just what's currently happening. And the way you do that is through events. All right, I think that wraps up the session for today. We have gone through everything. I'm going to hang out for 5 more minutes to answer any questions you might have. I'm going to play some light music. I'm going to put these 3 files onto GitHub somewhere and send it to you guys to look at afterwards. And yeah, I'm going to play some music, ask your questions in chat. I'm here for like 5 more minutes, and then we can carry on Discord if somebody has any more questions. Alright, why is there so much angry music? Is there a limit to write events? No. I mean, obviously, events also cost gas. They cost like some gas, so you can't emit like a million events in a single function because your transaction has a max gas limit and every block has a maximum gas limit. But generally speaking, like over multiple transactions, no, there is no limit. Like, emit whatever you want. Like ERC 721 contracts, they emit events every single time a transfer happens. And some famous NFT contracts, they have had millions of transfers happened, and that contract has emitted millions of events over time. But in a single function, like, yes, you can only emit as much events as like gas allows you to. I mean, that's still a lot. Like, you can probably still do like many hundred events in a single transaction, but you probably don't want to do that. Like, they still cost gas. It's just cheaper than storage. It's not free. Timestamps. Yes. So, Advanced Solidity Part 1, I did add timestamps. So, if you go to the LearnWeb3 DAO channel and you go to the Advanced Solidity Part 1 live stream, this one, I actually did add timestamps. So, you can look here. It has all these timestamps. So, mappings, memory versus storage, enums, blah, blah, blah. And I'm going to do the same thing with this one. So, don't worry, I will add timestamps. Casey. Oh, hey Casey, what's up? The bigger the smart contract, the more the gas fees. So, I mean, it costs money every single time you add something to storage, or rather, every single time you modify something in storage. So, like adding an element to an array of addresses, it's going to be the same gas cost every single time, regardless of if you're starting from an empty array or if the array already has 1,000 things. But every time you add a new address in there, it's going to cost gas, and that is more gas than it would cost you to probably emit an event. So, yes. But generally, the more storage variables you have in a contract, the more storage you're using upfront. Like when you write a contract and when you deploy it, the more variables you have, the more gas it's going to cost you to actually deploy the contract on the network. Because you're telling the network, I'm going to use this much storage. And they're all assigned a default value, right? Everything has a default value in Solidity. So you're kind of like, I mean, arrays start off as empty arrays, but basic variables like numbers, strings, addresses, things like that, they all have default values and they take up storage space. So the more variables you have, the more it will cost you to deploy your contract to the network. So, I mean, you want to reduce unnecessary storage as much as possible. And if you can replace something with an event, do replace it with an event. So don't store huge arrays of the history of past owners, and just do events. How do Uniswap contracts get upgraded? They don't. Contracts are not upgradable. You cannot change the code of a contract once it's deployed. When people say Uniswap v1, v2, v3, what they mean is they actually deployed entirely new contracts, and they changed their website to, instead of talking to the old contracts, the website now talks to the new contracts. You cannot do anything with you cannot upgrade code that has already been deployed. So if you actually go on Uniswap's website right now, they actually have two sections on their website, one for v2 and one for v3, and you can choose which one you want to use. So actually not here, it was here somewhere. I think this is for v2. I mean, you can search for Uniswap v2, and yeah, I think the default one is still set to v2, and then Uniswap v3 has like a separate interface, a separate website if you want to use Uniswap v3. I don't remember the link for it off the top of my head, but there is a separate there's a separate website if you want to use the v3 contract. But yeah, I mean, it's a different contract entirely. You cannot do anything. Will we have sessions in the future or deploying to mainnet? Is the same thing as deploying to testnet. The only difference is it's going to cost you actual money, because there are no faucets for mainnet ETH. You have to buy it with money, and it costs real dollars. But other than that, like, testnets and mainnets work pretty much the same way. On testnet, the only thing is like the ETH you use, the ETH you spend is meaningless. It's free. It doesn't cost anything. So like, you can do whatever you want. Whereas on mainnet, you're spending actual real money. So you only want to do a mainnet deploy if you're like launching like a product and you've tested your code thoroughly on testnets and you're sure that like there's no bugs or whatever, and you're deploying it to make it live to the public. But yeah, there is no difference. Like, you just deploy to a different network. But you pay with real money. That's the difference. All right. I'm gonna reg this. If there's any, maybe I'll take like one last question, and then I'm gonna rug it if there's no other questions. All right, I'm dead. All right. Cool. Yeah, I see no more questions in the chat, so I'm gonna go. Thank you everyone for joining. This was a lot of fun. I hope you understood what I said, and I will see you at the next one. And message me on Discord if you have any further questions. I will see you around. Enjoy your NFTs. Have a good day. Good night. Bye-bye.